The creation of a computer involves a complex, multi-step process that includes design, component manufacturing, assembly, testing, and distribution. Here's a breakdown of the key stages. 1. Concept and design. Engineers and designers define the purpose, specifications, and architecture of the computer. Key considerations include processing power, storage capacity, form factor, energy efficiency, and cost. Prototyping and simulation software are used to test concepts before production. Component manufacturing. Processor, CPU and GPU. Companies like Intel, AMD, and NVIDIA design and manufacture microprocessors using nanometer-scale semiconductor fabrication. Motherboard, designed with integrated circuits, power regulators, RAM slots, and expansion slots. Memory, RAM and storage. RAM chips are created using silicon wafers, while storage devices, HDDs and SSDs, are manufactured with magnetic or flash memory technology. Power supply unit (PSU) converts a C power into usable DC power for the computer's components. Display for laptops and desktops. LCD or OLED screens are manufactured separately and integrated later. Chassis case, designed for housing components and ensuring proper cooling. 3. Assembly. Components are assembled in factories using automated and manual processes. PCB assembly. Circuit boards are populated with chips, capacitors, resistors, and other electronic components. Final assembly. The motherboard, processor, memory, storage, PSU, and cooling systems are installed in the case. Software installation. BIOS UEFI firmware is pre-installed, followed by an operating system such as Windows, Mac OS or Linux. For testing and quality control, performance testing ensures the system meets design specifications. Stress tests check for overheating, power efficiency, and durability. Security and firmware updates are applied. 5. Packaging and distribution. Computers are packaged with accessories such as power adapters, manuals, and peripherals. They are shipped to retailers, businesses, and consumers worldwide. Detailed breakdown of computer creation process. The creation of a computer is a highly intricate process that involves multiple industries, cutting-edge technology, and extensive supply chains. Below is a comprehensive look at the stages involved. 1. Concept and design. Before manufacturing begins, a computer's purpose and specifications must be defined. Engineers and designers collaborate on intended use. Is it for gaming, business, AI processing, or general consumer use? Specifications: CPU, GPU, RAM, storage, display type, and connectivity. Form factor: desktop, laptop, tablet, server, or embedded system. Materials: aluminum, plastic, carbon fiber, and other materials are selected based on durability and weight. Thermal design: proper cooling solutions, air, liquid, vapor chamber, are engineered to prevent overheating. Prototyping and simulations. CAD computer-aided design software is used to create 3D models. Circuit simulations ensure power efficiency and stability. Functional prototypes are tested for performance and durability. 2. Component manufacturing. Computers are assembled using various components manufactured by specialized companies. The key components include a. Central processing unit, CPU, and graphics processing unit, GPU. Manufacturers: Intel, AMD, NVIDIA, Apple M Series, Qualcomm. Fabrication process. CPUs and GPUs are made from silicon wafers through a process called photolithography. Advanced chips are built using nanometer-scale nanometer technology. For example, 3 nanometers, 5 nanometers, 7 nanometers. Motherboard. Designed with integrated circuits, chipset, RAM slots, PCIe slots, and power regulators. Printed circuit boards, PCBs, are layered with copper traces and electronic components. C. Memory and storage. RAM random access memory. Uses high-speed transistors and capacitors. Storage: HDD, hard disk drive, magnetic platters and read-write heads. SSD solid-state drive. Uses NAND flash memory for faster speeds. D. Power supply unit PSU. Converts a C power from a wall outlet into DC power. Designed for efficiency standards, for example, 80+ certification. E. Display monitors, laptop screens. LCD. Older mini LED panels are manufactured separately and later integrated. F. Cooling systems. Includes heatsinks, fans, liquid cooling loops, and vapor chambers for heat dissipation. 3. Assembly process. Once components are manufactured, they are transported to assembly plants. The process includes printed circuit board (PCB) assembly, surface mount technology (SMT) places transistors, resistors, and capacitors onto the motherboard. Automated soldering fuses the components. Component integration. CPU is placed onto the motherboard. RAM modules are inserted into memory slots. Storage HDD SSD is connected. GPU, if dedicated, is installed. Cooling solutions are applied. Final case assembly. All internal components are enclosed in a chassis laptop shell or desktop tower. External ports, USB, HDMI Ethernet, are checked for proper alignment. For software installation and configuration, once hardware assembly is complete, software must be installed. BIOS, UEFI setup, firmware that controls the system at startup. Operating system installation, Windows, MacOS, Linux, or Chromios, is loaded. Driver updates. Ensures compatibility between hardware and software. Pre-installed software, productivity tools, security applications, and diagnostics programs. 5. Testing and quality control. Every computer undergoes rigorous testing to ensure reliability. Hardware stress tests. Simulates high-performance workloads to check for overheating or hardware failures. Tools like Prime95 FirmArc and MemTest86 are used. Connectivity and peripheral checks. USB, Wi-Fi, Bluetooth, Ethernet, and audio ports are tested. Battery life testing for laptops, tablets, simulated real-world usage to measure efficiency. Security and firmware updates. BIOS updates and security patches are applied. 6. Packaging and distribution. Once a computer passes all tests, it is packaged for shipping. Anti-static and shock-proof packaging prevents damage during transit, includes power adapters, manuals, and accessories, shipped via global logistics networks to retailers, businesses, and consumers. 7. Retail and consumer use. After reaching the market, users set up their computers by configuring personal settings, language, accounts, security, installing software and drivers based on their needs, updating firmware and security patches for optimal performance. Future trends in computer manufacturing. Quantum computing, research on qubits instead of traditional transistors. AI-powered processors, advanced neural processing units, NPS4 AI workloads. Sustainable manufacturing, use of recycled materials and energy-efficient designs. Chiplet technology, modular CPU-GPU designs for better scalability. An in-depth look at computer creation. Creating a computer is an extensive process that involves engineering, material science, high-precision manufacturing, and global logistics. Below is a deeper exploration of each phase, with a special focus on the intricate details of component fabrication, system assembly, and software integration. 1. Concept and design. Before manufacturing begins, extensive planning is required to ensure performance, efficiency, and user experience. The processor CPU, GPU, is the most complex component, involving nanometer-scale transistor manufacturing. Steps in CPU-GPU fabrication. Silicon wafer production. Pure silicon extracted from quartz is melted and formed into a cylindrical ingot. The ingot is sliced into ultra-thin wafers 300 mm in diameter. Photolithography process. UV light etches microscopic circuits onto the wafer. Transistors, logic gates, and interconnects are formed using layers of conductive and insulating materials. Doping and layering. Ion implantation alters electrical properties. Multiple layers of copper or tungsten are deposited for electrical connections. Wafer dicing and chip packaging. The wafer is cut into individual dies. CPU cores. Each die is tested, then packaged in heat spreaders for cooling. Key manufacturers. TSMC, Taiwan Semiconductor Manufacturing Company. Produces chips for Apple, AMD, Nvidia. Intel manufactures CPUs in-house using advanced 3 nanometers, 7 nanometers nodes. Samsung Foundry supplies high-end processors for mobile and computing devices. B. Motherboard production. Printed circuit board, PCB layering involves copper traces for connectivity. Soldering process. Automated surface mount technology, SMT places, transistors, resistors, capacitors. Testing. Electrical conductivity and durability checks. C. Memory and storage fabrication. RAM production. Uses DRAM dynamic random access memory technology. SSD solid-state drive. Production. NAND flash memory fabrication involves layering billions of memory cells. D. Power supply unit PSU assembly. Converts a C power from a wall outlet into DC power. Efficiency standards include 80+ certification for low energy waste. E. Display manufacturing. LCD panels. Use liquid crystals with LED backlights. Old screens. Use organic compounds for self-illuminating pixels. Used in high-end laptops. 3. Computer assembly. Once components are manufactured, they are assembled into complete systems. A. PCB assembly and integration. Motherboard testing. BIOS, UEFI chip pre-installed. CPU installation. The processor is secured into the socket. RAM installation. Memory modules are slotted in. Storage connection. SSDs or HDDs are connected via SATA or NVMe. Power distribution. PSU cables are routed for power supply. Cooling system. Fans, heat sinks, or liquid cooling solutions are attached. B. Final case assembly. All components are enclosed in a chassis desktop tower, laptop body. External ports, USB, HDMI, Ethernet, audio jacks, are aligned for usability. 4. Software installation and configuration. A. Firmware and BIOS setup. BIOS UEFI. Firmware is flashed onto the motherboard. Power on self-test post ensures all components function correctly. B. Operating system installation. Windows, MacOS, Linux, or Chromeos is installed. System drivers for CPU, GPU, networking, and peripherals are updated. C. Pre-installed software. Security updates and patches. Performance optimization settings applied. 5. Testing and quality control. Before shipping, the assembled computer undergoes rigorous quality assurance testing. A performance and stress testing. CPU and GPU stress tests. Ensures stability under high workloads. RAM testing. MemTest 86 verifies memory integrity. Storage benchmarking. Measures read, write speeds. B. Durability and environmental testing. Drop tests. Checks physical resilience. Temperature and humidity tests. Ensures operation in extreme conditions. C. Security and firmware. Validation. Ensures BIOS integrity. Security patches applied to prevent vulnerabilities. 6. Packaging and distribution. A protective packaging. Shock-absorbing materials prevent damage. Anti-static shielding protects electronics. B. Logistics and shipping. Computers are transported globally to retailers, businesses, and direct consumers. Warehouses and distribution centers optimize supply chains. 7. Consumer setup and use. Once delivered, the user sets up the computer. First boot and configuration. User account setup, language selection, software installation, applications, productivity tools, and games installed. Firmware updates. Ensures security and performance improvements. Future trends in computer manufacturing. A quantum computing. Uses qubits instead of transistors, enabling exponentially faster processing. B. AI-powered processors. Neural processing units. NPUs optimize AI workloads. C. Sustainable manufacturing. Use of recycled materials in chassis and packaging. Energy-efficient designs reduce carbon footprint. DI chiplet technology. Instead of monolithic CPUs, modular chiplets provide better scalability. Conclusion. The creation of a computer is a meticulous process involving innovative design and engineering. High-tech semiconductor fabrication. Precision assembly and software integration. Stringent quality testing and global distribution. A deep dive into computer manufacturing. The creation of a computer is a monumental feat of engineering, involving cutting-edge technology, ultra-precise manufacturing, and a globally interconnected supply chain. Let's explore each stage in even greater detail, with a focus on advanced materials, manufacturing techniques, automation, and future innovations. 1. Computer design and engineering. Before a computer reaches production, it must be meticulously designed to meet performance, efficiency, and market needs. A market research and user requirements. Companies conduct market analysis to identify trends in computing needs, for example, gaming AI, enterprise, cloud computing, consumer demands for performance, battery life, portability, and sustainability shape design decisions. B. Engineering and prototyping. 3D modeling and thermal simulation. Engineers use CAD computer-aided design software like AutoCAD, SolidWorks and Fusion 360. Finite element analysis via predicts stress points on materials. Thermal modeling simulates heat dissipation for cooling design. Material selection for durability and efficiency. Chassis materials: aluminum, carbon fiber, magnesium alloy, and high-strength plastic. Circuit board materials: fiberglass reinforced epoxy resin FR4 for insulation and durability. Cooling solutions: copper heat pipes, vapor chambers, and graphene thermal pads. Prototype testing: early prototypes are built using 3D printing, CNC machining, and injection molding. Engineers evaluate form factor, weight, and ergonomics. 2. Semiconductor and component manufacturing. At the heart of every computer are semiconductor chips, which power processing and memory functions. The manufacturing of these chips is one of the most complex industrial processes in existence. A. Semiconductor fabrication, CPU, GPU, RAM, and SSD production. 1. Silicon wafer production. High purity, silicon 99.9999999% pure, is extracted from quartz and melted into an ingot. The ingot is sliced into 300 mm wafers, polished to a mirror finish. 2. Photolithography, process etching circuits onto silicon. Wafers are coated with photoresist, a light-sensitive chemical. A UV laser etches nanometer-scale transistor patterns. The smallest chips today use 3 nanometers or even 2 nanometers transistors. Billions of transistors per chip. 3. Ion implantation, doping for conductivity. Ions are bombarded onto the wafer to alter silicon's electrical properties, creating transistors for layering and interconnects. Multiple layers of copper, tungsten, and aluminum interconnects are deposited for electrical pathways. Extreme ultraviolet lithography (EUV) allows for ultra-fine details in the circuits. 5. Wafer dicing and chip packaging. The wafer is sliced into individual dies CPU cores. Each die is tested, binned, based on performance, and encased in heat spreaders for thermal management. A. Purpose and market research. Companies analyze target audience, for example, gaming, business, AI, computing, general consumers, competitor models, and industry trends. Component availability and supply chain feasibility. Sustainability goals, for example, energy efficiency, eco-friendly materials. B. Engineering and simulation. C. Add computer-aided design tools such as AutoCAD and SolidWorks. Create 3D models. Thermal simulations test heat dissipation for cooling design. Structural integrity testing ensures durability. C. Choosing materials. Chassis materials: aluminum, plastic, magnesium alloy, or carbon fiber. PCB materials: fiberglass, copper traces, and epoxy resins. Heat dissipation: copper and graphite layers for cooling. 2. Component manufacturing. A. Semiconductor fabrication, CPU and GPU production. Key semiconductor manufacturers. TSMC produces chips for Apple, AMD, Intel in-house chip production. 3D transistor stacking. Samsung. High-performance SoCs for mobile and computing. B. Motherboard and PCB printed circuit board. Manufacturing. The motherboard is the backbone of a computer, connecting all major components. 1. PCB fabrication process. Multi-layered PCBs 6 to 12 layers are designed for signal integrity. Copper traces are chemically etched onto fiberglass layers. Surface mount technology SMT places tiny transistors and capacitors onto the board. Reflow soldering melts solder paste to secure components. 2. Power regulation and chipsets. Voltage regulators VRMS ensure stable power delivery to the CPU and GPU. Chipset controllers manage USB SATA and PCIe connectivity. C. RAM and storage manufacturing. 1. DRAM dynamic RAM production. Made using microscopic capacitors that store electrical charge. DDR5 RAM is currently the industry standard for high-speed memory. 2. SSD solid-state drive. Manufacturing. Uses NAND flash memory to store data electronically faster than 3D NAND stacking allows for more storage in a compact space. DI cooling system manufacturing. Copper heat pipes and vapor chambers transfer heat away from the CPU GPU. High-end gaming laptops use liquid metal thermal compounds for better conductivity. 3. Computer assembly and automation. Once all components are manufactured, They are assembled into complete systems using a mix of human labor and robotic automation, a CPU and GPU installation. The processor is placed into the LGA LAN grid array, or PGA pin grid array socket. Thermal paste is applied, and a heat sink or liquid cooling solution is mounted. RAM and storage installation. RAM modules are slotted into DDR memory banks. SSDs or HDDs are connected via NVMe PCIe or SATA interfaces. Power supply and cable management. PSU, power supply unit cables are routed for optimal airflow and aesthetics. Modular power supplies reduce excess wiring. Robotics and automation and assembly. AI-powered robotic arms handle delicate motherboard assembly. Automated optical inspection. AOI ensures flawless soldering. 4. Software integration and testing. Once assembled, the system is tested and loaded with software. A BIOS UEFI configuration. The firmware low-level system software is installed to initialize hardware. BIOS installation and driver updates. Windows, MacOS, Linux, or Chromios is loaded onto storage. Device drivers are installed for graphics, networking, and peripherals. Performance and stress testing. CPU benchmarks. Prime 95. GPU benchmarks. 3DMA, RK battery life tests for laptops. 5. Packaging and global distribution. A protective packaging. Anti-static bags prevent electrostatic discharge. Foam padding and shock-proof casings protect delicate components. B. Global logistics and supply chain. Computers are shipped via air freight, cargo ships, and distribution centers. 6. Future innovations in computer manufacturing. A quantum computing uses qubits instead of binary transistors, exponentially increasing processing power. B. AI-powered processors. Neural processing units NPUs for machine learning acceleration. C. 3D chip stacking and chiplets. AMD and Intel are developing multi-die chiplet architectures for better efficiency. DI sustainable computing. Companies are moving towards recycled materials and carbon-neutral manufacturing. Final thoughts. The creation of a computer is a remarkable blend of physics, engineering, automation, and software development. Each stage from semiconductor lithography to robotic assembly pushes the boundaries of human innovation. Great choice. Let's dive deeper into some of the exciting future technologies in computer manufacturing, including quantum computing, AI-driven chip design, and sustainable computing. 1. Quantum computing. Quantum computing represents a radical departure from classical computing. Instead of relying on binary bits, 0 south and 1 south, quantum computers use quantum bits qubits, which can exist in multiple states at once due to the principles of superposition and entanglement. How quantum computing works. Superposition. A qubit can represent a 0, a 1, or both 0 and 1 simultaneously. This enables quantum computers to perform many calculations in parallel. Entanglement. When qubits are entangled, the state of one qubit is directly linked to another, even if they are separated by large distances. This allows for faster communication and processing of complex information. Quantum interference. Quantum states can interfere with each other, either reinforcing or canceling out. By controlling these interference patterns, quantum computers solve problems much faster than classical computers. Challenges in quantum computing. Qubit stability. Qubits are extremely sensitive to their environment, making them prone to errors. Maintaining qubit coherence long enough to perform meaningful computations is a challenge. Error correction. Quantum error correction is a crucial field of study. Since quantum computers are highly error-prone, robust error correction methods are necessary for practical use. Scalability. Building quantum computers with enough qubits to solve real-world problems requires massive amounts of processing power. Cooling and precision engineering. Potential applications. Cryptography. Quantum computers could break current encryption schemes, but they could also lead to new forms of quantum encryption that are more secure. Drug discovery. Quantum simulations could revolutionize the pharmaceutical industry by simulating molecular interactions at an atomic level, speeding up drug discovery. Optimization problems. Quantum computing can handle optimization problems that involve vast amounts of variables, such as supply chain logistics or climate modeling. Key players in quantum computing. IBM Quantum, leading the development of quantum computing hardware and software platforms. Google Quantum AI, famous for achieving quantum supremacy with their 53-qubit Sycamore processor. Intel, developing Qbot systems using silicon-based technology. D-Wave Systems focuses on quantum annealing, a technique for solving specific types of optimization problems. 2. AI-driven chip design. Artificial intelligence AI is playing an increasingly important role in hardware design. AI and machine learning techniques can optimize the design of semiconductors, making them faster, more efficient, and cost-effective. AI-assisted chip design. Traditional chip design challenges. Traditional methods of designing chips rely heavily on human expertise and trial and error. These methods can be slow, costly, and not always optimized. AI-driven automation. AI can accelerate the chip design process by using machine learning algorithms to identify the most efficient architectures and configurations. AI can also simulate and test various designs in virtual environments, greatly reducing the time and cost associated with prototyping. How AI helps in chip design. Layout optimization. AI can suggest the most efficient transistor placements on a chip, minimizing power consumption and reducing heat generation. Design rule checking (DRC). AI algorithms can automatically check if a design adheres to the manufacturing constraints, reducing the likelihood of defects. Chip simulation. AI can simulate the performance of a chip before it is physically fabricated, allowing designers to test multiple iterations and select the best configuration. Automated verification. AI can verify the functionality of the chip, ensuring that it performs the desired tasks correctly, reducing human error in the design verification process. Examples of AI in chip design. Google's Tensor Processing Units, TPUs. Google uses AI to design their custom TPUs, which are highly optimized. NVIDIA's AI-based GPU development. NVIDIA has utilized AI to create GPUs that are faster and more efficient for AI workloads. Cerebras Systems. The company uses AI to design massive-scale chips for AI workloads, featuring huge cores that contain thousands of processing units. Advantages. Faster time to market. AI-driven chip design allows for faster iteration cycles and quicker time to market for new hardware. Power efficiency. Optimizing chip designs using AI can result in more energy-efficient processors, crucial for reducing the environmental impact of high-performance computing. Customization. AI-driven approaches enable companies to create customized chips tailored for specific tasks, such as AI gaming or data center operations. 3. Sustainable computing. The demand for computational power is growing exponentially, but so is the environmental impact of computing. Sustainable computing aims to reduce energy consumption, minimize electronic waste, and ensure that computer manufacturing and operation are environmentally friendly. Strategies for sustainable computing. Energy-efficient hardware. Low-power chips. Companies are designing processors that consume less energy while maintaining high performance. For example, ARM processors are known for their power efficiency, and companies like Apple use ARM-based chips in their products. Energy-efficient cooling systems. Liquid cooling and vapor chamber technologies are replacing traditional air cooling methods, which consume a lot of energy. Some companies are even experimenting with immersion cooling, where components are submerged in special coolants. Be recyclable and eco-friendly materials. Recycled materials. Manufacturers are increasingly using recycled aluminum, plastics, and other materials for computer cases, circuit boards, and packaging. E-waste recycling. Proper recycling of electronics is a key focus. Materials such as gold, copper, and rare earth metals are being recovered and reused. C. Carbon neutrality. Carbon offset initiatives. Many tech companies are committing to becoming carbon neutral by offsetting their emissions through renewable energy projects and other sustainability initiatives. Green data centers. The shift to renewable energy sources such as solar and wind for powering data centers is helping to reduce the overall environmental footprint of cloud computing. Notable examples in sustainable computing. Apple has committed to using 100% recycled aluminum in its Combo MacBook and has a zero carbon emissions goal for its entire supply chain by 2030. Google has been carbon neutral since 2007 and is investing in renewable energy to power its data centers. Microsoft has pledged to remove all its historical carbon emissions by 2050 and is heavily investing in sustainable hardware design and energy-efficient data centers. The future of computing. Quantum computing will solve problems that were once unimaginable, potentially transforming industries such as cryptography, healthcare, and artificial intelligence. AI-driven chip design will enable the creation of highly specialized and efficient processors tailored for different applications, significantly improving performance in everything from gaming to AI. Sustainable computing will become the standard as the tech industry continues to innovate in energy-efficient hardware, recycling practices, and carbon neutrality.